Okay. So once again, independent events are two events that do not affect each other. They were completely separate. Flipping the coin, getting the 6 on the dice, me being able to do a backflip and finding a red car in the parking lot. Separate events, two completely independent. Whenever you were trying to find the probability of both of them, we just had to find the probability of A multiplied by the probability of B. So that was independent. Alex, now what was mutually exclusive events?
Two events that cannot happen at the same time.
Good, sorry. So cannot happen at the same time. That is mutually exclusive, not independent. Mutually not independent. Is this I'm not sure.
Look on the bottom one.
I would assume yes, probably except for the top.
Canister contains at least 50% recycled materials, 15%.
So cannot happen at the same time. So if two events cannot happen at the same time, and we're trying to figure out what is the probability of both those events happening, what was that?
0.
Big old 0. And if it's impossible for both these two things to occur at the same time, it's impossible to get both of them to happen at the same time. So it's big 0 is probability every time. Once again, that little upside down U means and. Are we okay with that from yesterday? And then the last thing was we were looking at these OR statements. The probability of A or B. That little U represented our union again. So the probability of A or B. How did we find these yesterday? It was like the vowels, like picking out the vowels from the alphabet, but also picking out the letters from math.
Didn't we add them?
So we added them together. So we found the probability of A plus the probability of B. What also did we need to remember?
Overlap ones to subtract.
So sometimes we have a little bit of an overlap. Sometimes it was possible for there to be A and B at the same time. And so if you calculated A and calculated B and added those two together, you were counting that A and B twice. So for example, with the vowels and the letters from the word math, we calculated all the vowels. We found the probability of getting a letter from the word math. But we had A twice. A was a vowel and it was a letter from the word math. So we always had to subtract by that overlap to make sure we weren't counting those letters or getting those double letters. We okay on this one? So that was what we did yesterday. So now we're going to talk about frequency tables. I don't have notes for you today like I did yesterday, so I apologize for that. But we're going to look at frequency tables. So we're going to look at some tables and figure out how can we pull probabilities from these tables, or how can we figure out what are the values of each of these numbers from these tables. Oh, I haven't done any stuff. Get that away. There we go. Okay. So with frequency tables, what a frequency table is it's going to have two-way frequency table is going to have some pieces of information. You're going to have some sort of category, and then you're going to have the results for those categories. And a two-way frequency table will always have two categories. We'll always display two different types of categories. So in this case, we have this table. It's looking at, it has sort of how many students have taken a driver's ed class, how many students did not take a driver's ed class, and then how many students passed the driver's ed test, or how many students passed the driving test, and how many students failed the driving test. And using this frequency table, we want to see, can we make any conclusions about how the driver's ed class affects students, and how it affects their ability to take the test? So students that take the driver's ed class fail more? Well, based off this frequency table, what conclusions can we make about the driver's ed class? More people who passed took it. So if we look at the people who took this class, we have 32 compared to 7 for pass versus fail. But people who did not take the class, we had 18 passed and 23 failed. So we had more people passing, or a better ratio of passing, in the people who took the class compared to the people who did not take the class. So just from this table, we can make some quick inferences about taking that class should be better for you for passing. Should be. Doesn't necessarily mean it always is. Sometimes you might get those students who take the class and fail. But it should be better for you in this case. So that's just reading a frequency table. Now we're going to talk about how can I use this to actually make some probabilities. How can I figure out what is the probability? Are we okay with this? So before I move on, quick caveat, I pulled these questions, I pulled all these charts from the textbook and from state tests. So if you make any question, or if you dislike the fact that I only have male and female up here and don't have any other genders, I pulled these from the state, so don't blame me, I stole these from someone else, okay?
Did someone say something about the gender?
No, someone or another person in another geometry class made a joke yesterday about like there should be more than the two gender, or if it was about mutually exclusive. And he's like, okay, so if they had gender on there as mutually exclusive, should I put that as 0? Because I know this is kind of political, and I said typically they will tell you, or they shouldn't have something like that on your state test or something like that. But he was worried about the state test. But okay. I just want to put that caveat that I didn't necessarily create these tables; these were taken from something else. So. But yes, but if that were to occur, it should say whether they're mutually exclusive. If they show you a table, each of those categories should be mutually exclusive necessarily between those two. But I understand if you prefer there to be more genders than just that's okay. That caveat aside, let's look at this table. So this table shows student involvement at a local high school in their extracurriculars. So it's split up in whether students are involved in extracurriculars or whether they're not involved in extracurriculars, and then also splits it up by whether they're male or female. So using this, what would be the probability that I went to this high school and I randomly pointed out a student? What would be the probability that student was a female? Just any female. I don't care if they're involved in extracurriculars or not involved in extracurriculars. I just want the probability of finding a female student.
259 over 516.
Good. So there's 259 total female students out of 516 total students. So 259 divided by 516 should give us like 0.501, just a little bit above 50%. Or 0.502 or something like that. So that's how many students are females at this school, or the probability of being female. What would be the probability of randomly picking a student and that student not being involved in any extracurricular activities?
265 over 516.
265 over 516. Good. So the probability of not being involved would be 265 over 516. And that's because we have 265 total students who are not involved in activities, and then 516 total students in the entire school. Good. Last question. What if I wanted to pick a random student? What would be the probability of that student being female and not being involved in any activities?
139 over 2.
Female and not involved in school activities.
Over 260. Over 250.
So
Or is this go over everyone?
it would still be over everyone.
Over 112 over 516.
So our students that are female and are not involved in activities is going to be this box right here. Those are all the females that are not involved in activities. 120. This is the probability of female and not involved. It's one of those and statements again that we talked about yesterday. But once again, we're just looking at all of the students in the class, or all the students in this high school. And so it's the 120 is how many desired outcomes I have out of all of my total students again in out of the box. So 120 divided by 516 gives me 0.2. Are we okay with that, Morgan? So that clarify a little bit. Okay. Once again, it's number of students that are female and not involved. We're looking for where the intersection of both of those categories are, and then add, because we're still asking out of all of the total students. If we wanted to figure out of all of the students that were not involved, we would then use that 260 or 269 or whatever number you were looking for. Okay. So this table shows the number of male and female students by grade level on a prom committee. So you have your prom committee, you figure out, okay, how many students, what's the grade of each of these students, and whether they're male or female. So you have your juniors, you have your seniors, you have your males and your females. and then you have your totals for each of those rows and each of those columns. You want to find what is the probability of randomly picking a student and that student being a male and who is a junior. The probability of randomly picking a student that is a male and who is a junior. Take a moment, see if you can come up with what that probability should be. All right, someone walk me through this question. What did you do for this problem?
Number of students is 12. And then looked at like the specific, like male and then juniors. So I just took like,
Okay, so we saw the intersection of male and juniors. Those are the students we're looking for. We saw there were 3 students that fell under that category. And then we're taking out of the entire prom committee, so we look for all the total number of students in that prom committee, which was 12. And so 3 out of 12 gives us 0.25 as our probability, or 25%. Okay on that one? Where we came up with those numbers? Cool. All right, so now we're just going to take it one step further. Just a little step further. We're going to talk about what's called conditional probability. So if you're looking for the probability of an event after or given that an event has already occurred, it's called conditional. So we're looking at what is the probability of this happening after you know something is already true, or after you know this thing has already occurred, or after you know this thing is already effective. That's called conditional probability. So it's event A given that I already know event B has occurred. So we write the conditional probability of event B. You would say this is the conditional probability of event B given that event A has already occurred. We write that as this A, or we do probability, from the parentheses, B, we have this slash here. That slash means given. So this is what is the probability of getting event B to occur given that A has already happened. The main signifier of when it's going to be a conditional probability is typically in the question, they will say given. If they have that word given in there, you can pretty much always assume, oh, I know this is going to be a conditional probability. I should jump right to my conditional probability. Not always will say given, but if it ever says given, then that should be a sign like, oh, it's going to be a conditional probability. I know that's my case. And so that's always like a big sign to look for. So if we look at this, it has a lot of words on it, and it's a big text, but that's okay. So the respondents of a poll were asked whether they were for, against, or had no opinion about a bill before the state legislature that would increase the minimum wage. So they asked a bunch of people, they said, okay, are you for, against, or do you have no opinion on increasing minimum wage? They pulled all their results, and then they split these people up into some age groups. So they had 18 to 29, 30 to 45, 46 to 60, and over 60. And then they said, are you for, against, or no? And so they calculated all this information on these 1,000 people that they asked. And so we want to try to figure out what is the probability that a randomly selected person is over the age of 60, or 60 years old or over, given that this person had no opinion about the state bill. So once again, seeing that word given in there, that should be a sign that this is going to be a conditional probability. So it's the probability that this person was over 60 given that they had no opinion about this bill. So we're trying to find that probability. So with conditional probabilities and with these two-way frequency tables, so with conditional probability and with these two-way frequency tables, as soon as it says given, it's narrowing down our results. So as soon as it says given, we're no longer caring about everyone, we're just caring about those people who fall under that given result. So we know our person that we have in front of us. We know they have no opinion about the bill. So we know they have to fall within this category. They're not. We don't care about the for or against people anymore. We don't care about the totals. We're just worrying about people that fall in the no opinion category, because that was our given statement. Now we have to figure out, okay, how many people were over 60 and had no opinion?
40 over 100.
40. So 40 over 100 would be our conditional probability. Because we're looking, what is the probability of that person being over 60, which was 40, and having no opinion? Sorry, I wrote the wrong number. So being over 60 and having no opinion, we have 40 people who fell in that category. And then we know they already have no opinion, so we're just looking at that 100 people. So 40 over 100 would be 24. Seem okay? Amanda? We talked about conditional probability, which a conditional probability is if you're looking for the probability of some event happening after you know something is already true. So in that last example was, what was the probability of me randomly picking a person that was over the age of 60 after I already knew that they had an opinion on something? So this little line here means given. This is typically how we write a conditional probability. It will be P, or probability of B, given that event A has already occurred. And it will always say that given statement. I should always try to tell you what that given statement is in the question. It won't always say the word given, but if it ever does, that should be like your red flag. Oh, this is a conditional probability. I need to think about that. Let you get that down. So what we looked at on this piece right here was we had all these people who were told about this bill. They were for, against, and no opinion. So because we were looking for what is the probability that a randomly selected person is over the age of 60, given that they had no opinion, that given statement told us we just need to worry about the people with no opinion. So as soon as we saw it had given, we're just looking at what the given statement is. And then the people over 60 and no opinion, which is 40. So 40 I found. I know that was a quick run through, but are you okay with that? Okay. We'll see a couple more examples of this as well. So, same graph, same thing. But now we want to figure out what is the probability that a randomly selected person is between 30 and 45 years of age, given that the person is in favor of the minimum wage bill. So because we're looking for strictly in favor of, we're just looking at people who are for the bill. So that we're narrowing it down to this one column. And now, because we're just looking for people of the age 30 to 45, it's just going to be that 200 people out of that column. So 200 out of our 780 will be our probability. So conditional probability of for the bill, or sorry, conditional probability of 30 out of 45, given that they were for the bill, is equal to 200 over 70. Now, conditional probability of being between 30 to 45 for the bill is different from the probability of finding a random person that's for the bill, given that they're 30 to 45. So if you switch these around, it changes the probability. Now, rather than looking at the for the bill column, we're looking at the 30 to 45. So if we flip-flop those, that can change what the question's asking as well. It changes that given statement that you're right now. So let's see if we can do this last one, and then we'll talk about the little activity I have. So what is the probability that a randomly selected person is not 18 through 29, given that the person is in favor of the bill? So not 18 through 29.
So what would you do? So would you do 30, 60, 100%, like switch, like get them out?
So Once again, because it's given that we're for the bill, we're only looking for this for the bill column. And because we're looking for people who are not in favor, because we're looking for people who are not 18 through 29, we want all of these people, all the people that are not 18 through 29. So you do the 780 minus the 310, which will give you 470. And so 470 people out of 770. Look at this. Which should be something like 0.60 or something. Are we okay with that? So when there's a given statement, narrow down your column or narrow down your row to that specific piece, and then look for, okay, what is that piece that they're looking for inside of that whole row, inside of that whole column, rather than trying to look at the entire table at once. Okay. Do that, we'll have to stop that.